Okay, so Newton's first law, guys, is very, very simple, right? It's part of rocket science, but it's not rocket science. Okay? Really, really simple. In fact, so simple that Newton summed it up in one word. That word is inertia. Okay? The idea of inertia is Newton's first law. Okay? So what inertia tells us, okay, is it tells us that an object that is like this desk, for example. Okay? So Newton's first law says that this desk, unlike that desk, this desk is going to stay right there, provided I don't do anything to it. See what I mean? Not rocket science. Of course the desk is going to stay there if I don't do anything to it. It's an inanimate object. If there's no forces that are not balanced acting on it, it's not going to go anywhere. Everybody follow me on that?
Yeah.
Okay? So that's what Newton's first law says. It also says, though, that an object traveling at a constant velocity will continue to do so unless acted upon by an external unbalanced force. Okay? So if I had an object, let's say, floating through space, where there's no friction, no air resistance, or anything like that, that object should continue to float through space forever. Now, does anything actually ever do that? No, because there are actually forces in space, right? If you get close enough to something, you'd be attracted to it gravitationally. Maybe you go through a cloud of gas and there's some resistance or whatever. But we're saying that in the absence of any other forces, an object will continue to do what it was already doing. That is, it will stay at rest, if it was at rest, and it'll continue moving at a constant velocity, if that's what it was doing before. Okay? Something will only change its velocity if it's acted upon by some force that's not balanced. Because actually, right now, this desk is being acted upon by two forces. Gravity and... Nope. Gravity and the floor. Okay? Because if there was no floor, what would this desk be doing? Falling. Okay, so there's something that Newton came up with in his third law, okay, called the reactive or normal force. When gravity pulls the desk into the floor pushes back with a force equal to gravity. That's why the desk doesn't move. Okay, everyone with me on that? Okay, that's actually the force you feel right now in your butt, sitting at your desk. Okay, gravity's pulling you down into your seat, and the seat's pushing back. The longer you sit there, right, you notice that, right? You notice that this force has been acting on you in response to gravity pulling you down. Well, your feet get tired if you've been standing for a long time. Okay, your feet have to work against the force of the floor pushing back against you. Okay? All right. So inertia, very simply, is what an object will continue doing whatever it's doing as long as there's no unbalanced forces acting on it. Now that can be a problem. If you're an astronaut, it can be a real problem. Okay? To move around in space, you have to have some kind of propellant or a tether, or both. Okay? If you don't, and you become separated from your ship, what will happen to you? You'll float away, and there'll be nothing you can do about it. Flailing like this in space doesn't do anything. It doesn't do much on Earth either. Okay? But in space, it does even less. Okay? There's no force out there for you to work against. So there's nothing you can do. Okay? You just float away. Everyone kind of follow me on that? I'm going to show you a video about that in a little bit. Okay? Why Newton's first law is bad for you in space and you're an astronaut. Why you should always be tethered, okay, to something or have propellant, enough propellant to get around. All right. Inertia is related to the mass of an object. The more massive an object is, the more its tendency is to keep doing what it's doing. Okay? When you think about it, if you got a ball rolling towards you at like 10 kilometers an hour, you just put your foot up, you can stop it. If you have a bus rolling towards you at 10 kilometers per hour, putting your foot out is not going to result in very much good, is it? Okay? Because that bus has way more inertia than the ball did. Okay? It's about mass. All right. And obviously we talked about this already as well. Understand that changes in inertia require force. Okay, so if I'm going to change something's velocity, I have to have an unbalanced force acting on it. Okay, so like with this desk, for example, okay, as soon as I have an unbalanced force acting on it, it moves. But as soon as that unbalanced force is gone, it stops. Well, actually, it doesn't stop. It stops because there's another unbalanced force. Once I let go, there's the force of, well, not so much gravity in the floor because it didn't lift it. I just pushed it. It's just friction, right? Friction resisted it and pulled it back to a stop. And then it stopped, and now all the forces were balanced. Everybody all right with that idea? Okay. So what we need to understand first off is what exactly is a force. Okay? So a force is a push or a pull. Very simple. Okay? It's anything that can push or pull. So a tow truck that is towing a car, okay, is using a pulling force through the cable. Okay? If we're talking about a baseball, okay, gravity is a force that causes it to follow a projectile arc. Okay, we talked about projectile motion in the last unit. The reason that happens is because of gravity. The force of gravity is even on it all through the arc. Okay? Or a push, like a bulldozer pushing over a wall. Okay? Those are all forces. Okay. Now, force is a vector quantity because I don't just say I pushed something. I usually say I pushed it left, right, forward, whatever. Okay, I gave it a push in that direction. Okay, force is a vector quantity, so it's going to work just like displacement and velocity and acceleration. Okay, have in the last unit, so there will be some vector stuff involved here. Okay, now mass. In North American and well, all North American countries for sure, and even in some European countries, there's this idea that mass and weight are the same thing, and they're not. Okay? How much, and the reason that we have this misconception is because when we step on a scale to weigh ourselves, we are using a force to tell us our weight. The problem is the scale doesn't tell us our weight, it tells us our mass. Okay? Weight is a force. In fact, it's the force of gravity. Okay? I weigh a certain amount here. But if I went to the moon, I would weigh less. Even though there'd be just as much of me on the moon as there is here. So weight is a force. It's dependent on the gravitational environment that you're in. Mass is how much of you there is. That's just dependent on how much matter makes you up. Okay? So if you're going on a diet to lose weight, don't. Go to the moon. You'll weigh less. Okay? You just want to lose weight. Just go somewhere where gravity isn't as strong. You'll weigh less. You want to lose mass? Okay, that's going to be harder. Right? Then you got diet and exercise coming into play. Okay? That means I'm actually making less of myself. Or if I want to bodybuild, more of myself. Okay? I'm going to put on more matter, more mass. I'm going to take off some matter, less mass. Your weight, you can calculate. Okay? Because force of gravity is your weight. So you go m times g. You take your mass and you multiply by the acceleration due to gravity, and that'll give you your weight in newtons. Okay? Mass in kilograms. Okay? So a newton is the unit for force, and it's a kilogram meter per second squared. We'll talk about that another day. But okay, yeah, that's how you calculate your weight. Right? So mass, okay, has to do with how much of you there is, how much matter you possess, and mass is scalar. Okay? I don't say my mass is 72 kilograms down. Okay? Because it isn't. My mass can go any direction I want it to go. It's whatever way I'm going. Hey, my mass doesn't have a direction. It's a scalar quantity. It's how much of me there is. Okay? But my weight, on the other hand, is a force. And that force is directed down because gravity is what's causing that force. It is that force. All right, so obviously the difference between a penny and a supertanker is that one has a lot of matter and the other has very little. And one has value and the other doesn't because no one uses pennies anymore. Right? Yeah. What's that?
Would they be the same weights?
No. It's mass times 9.81. I could make them the same weight if I threw this in a black hole. right? Where gravity was, a million times Earth's gravity. Then this could weigh as much as the super tanker. Okay? That would be somewhat impractical.
I'm sure it's right. It says that weigh 1,570 pounds.
Newtons, not pounds, newtons. And no, that doesn't seem right because your mass in kilograms is what?
40. Like 70 something?
Yeah, that seems about right. 70 times 9.81.
Yeah, that's right.
That's not 1,500. That's like 600 and something. Your weight isn't in pounds. Your mass is in pounds. You can't convert your weight back to pounds. Your weight is a force. It's in newtons. See, you're having that problem right now. That's a cultural problem that we have where weight and mass are the same thing. They're not. Okay? Now, incidentally, if you ever want to make somebody feel really uncomfortable, okay, because some people are really dumb and they don't have like social cues. So at a party or whatever, hey, how much do you weigh? That's a really indelicate question, by the way. Okay, so if you've ever asked somebody that, don't. It's a really indelicate question. Okay, when somebody asks me how much I weigh, I tell them in newtons. And then either they think I'm crazy and they go, and they walk away and I don't have to talk to them anymore. Okay? Or they're like, what do you mean? And then I tell them, that's a really indelicate question, but I told you the right answer, but you're too dumb to know it. Okay? Yeah. So don't ask people how much they weigh. That's not very nice. If someone does, tell them exactly how much you weigh. Okay? I tell them I weigh 750 newtons, and then they go, what now? And then I haven't lied. I told them exactly the truth. And they won't ask me anymore, and they'll have no idea how much my mass is, which is what they really wanted to know anyway.
You say that to like your doctor?
No, I wouldn't. You know why? Because my doctor would already know because I step on the scale and they're fixing my weight anyway. My mass anyway.
What if you like have to like tell them your weight? Would you tell them?
You know what? My doctor would know the difference. Doctors are pretty smart. If I told him my weight, he'd go, "You're a smart ass," and he would change it. Okay. So, here's the big thing, guys. Weight and mass are different. Okay? So weight is a force, and that's what we just talked about. It's the force of gravity pulling on your mass. Okay? Certainly if you have more mass, you will have more weight. Okay? A bigger person weighs more than a smaller person in the same gravity environment. Right? But it would be possible for somebody 6 times your mass, if that's possible, okay, to go to the moon and actually weigh less than you do on Earth. Okay? Again, it's about the environment you're in. That person still has 6 times your mass, but now they don't weigh as much. Right? And that was a problem that the Apollo astronauts had when they went to the moon. Even with all their gear, okay, the big, heavy spacesuit and everything, they were still considerably lighter than they were on Earth, and they actually found walking and moving around to be quite difficult because when they would push, they would kind of fly up off the surface a little bit, almost like they were jumping, even though they just meant to walk. Okay? Because when we walk, we actually push upwards a little bit when we walk. Okay? So they're doing this in their spacesuits, and they're kind of lifting off the surface, and they didn't want to fall. Okay? If you fall and you hit your faceplate on a rock, you die. Okay, because you explosively decompress, and that's bad. Okay, so they had to actually learn how to move differently. They had to walk very differently. In fact, if you ever watch when they're trying to go fast on the moon, they do this little shuffle thing. Okay, because they're moving more horizontally than they are vertically. Okay, and as a result, they don't have to worry of falling as much. Okay?
If you fell from a high point on the moon, would you get hurt less than if you fell on Earth because of
Yes,
gravitation?
you would. Yeah, you would get hurt less. So if I fell, let's say, from the roof here on the moon, it wouldn't hurt me. I'd be able to actually land like I would on Earth quite easily. Okay, but if I tried that here, I'd probably break my leg. Okay, or many things. Okay, but yeah, on the moon, I wouldn't reach the same velocity by the time I reach the ground because the pull of gravity is less, and I weigh less. Okay. So when you are going to the gym, okay, and you're lifting weights, remember that you're really lifting mass, okay? That's why they don't have these on the International Space Station. You can't lift weights on the International Space Station because they don't weigh anything, okay? They have mass, but they're a real problem, okay? If you took a barbell and a big weight bench onto the International Space Station and went to do bench press, what would happen?
Your body would go up.
Your body would go up. Yeah, you'd push on the bar, and then the bar would pull you. And it would look really cool, like at first, because you could put as much weight as you wanted on there. Then get it moving, and then it would just up across the station you would go, because there would be no gravity to stop it. And you wouldn't be able to stop it because, well, you're not attached to anything. So on the International Space Station, they actually have something that's like a Bowflex. It uses resistance as opposed to weight, okay, in order for them to get resistance type of exercise.
You see in movies all the time that they have those like anti-rotational things. Is that
Yes.
real thing?
Yes, we're going to talk about that in Unit 3 actually, generation of artificial gravity with a spinning drum. Yeah, it does work. Yeah. There's problems with it that science fiction tends to overlook, but yes, theoretically that would work. The problem is there's conservation of momentum. So if one part of the ship is spinning, the other part of the ship is going to want to spin too, and we have to have something that can offset that. Okay, making sense there. All right, we're going to watch the video of what's bad about Newton's first law here. Okay, so now that we've seen those videos, especially the smart car hitting the concrete, okay, we can see mass is pretty important in terms of Newton's first law. The more mass you have, the more inertia you have, and as a result, the better you're going to do in a crash. Now, I'm not saying that wearing your seatbelt isn't important and airbags aren't important. They are. They're critical safety systems. Okay, your crumple zones in your car, critical safety system, right? But in the end, it's all about mass. Okay, and the more of it you have, the better off you're going to be in a crash. That's why a guy that drives a semi-truck doesn't get hurt, okay, in a crash. He's just got too much mass. Okay, unless of course the trailer folds right on top of it. Right, then yes. But. Okay. So if we're looking at Newton's first law, okay, and we can think of this a little bit like if we're using hockey or paint drying, I mean curling as an example here. Okay, so if you have something sliding along the ice, and the ice is perfectly frictionless, then that thing's velocity is going to remain constant. Okay, so obviously in the real world there is friction on ice, and things do stop, like in paint drying. I mean curling, the rocks do eventually stop, and everything is kind of dependent on that. Okay, but in the perfect physical world, if the ice was perfectly frictionless, these things would just continue moving. Now, if I'm playing hockey and I go to hit the puck or shoot the puck, okay, I'm going to have to apply a force to it. Agreed? Okay, so as soon as my stick touches the puck, its velocity is going to start what? Increasing or changing. And it'll continue to accelerate as long as the stick is doing what? Touching the puck. As soon as the puck leaves the stick, it's now going to, okay, well let's say it's on perfectly frictionless ice. Once I just shoot it along the ice, then it'll travel at a constant velocity after that. You're right, in the real world, the instant it leaves the stick, it's actually starting to slow down already. Okay? But it's only going to be accelerating while the force is active. Okay? Once that force is gone, then we're back to a Newton's first law situation. Right? You can actually see this in this video. Okay, so I got this video here. I can't record it. As we can see, okay, you can see that we were getting that puck to accelerate fairly well. Okay, and there's a fair amount of technology that goes into the design of the stick, and then a fair amount of practice, obviously, that goes into the technique of applying your weight and getting your center of gravity over the puck and all that stuff that Phil Kessel was doing in that video in order to get a good hard shot, okay, off of that puck. Right? But obviously, once the puck leaves the stick, it's traveling at a constant velocity. Any situation where all the forces are balanced is a Newton's first law situation. Okay? Anytime there's an unbalanced force, then we're talking about a Newton's second law situation, which we'll talk about tomorrow probably. Okay, so Newton's first law is stated like this. Okay? An object at rest will remain at rest, and an object traveling at a constant speed will continue to do so unless acted upon by a net or unbalanced force. So if I add all the forces together, okay, considering their vectors, and it adds up to 0, then the net force is 0, and we're dealing with a Newton's first law situation. If I add the forces together and it's not 0, like it is in this situation here with the book, okay, if I apply a force of 18 newtons to the right and 20 newtons to the left, the net force is 2 newtons to the left, and this object is going to accelerate to the left, right, because of that net force. Okay? So net force works like your net pay. If you have a job and you've ever gotten a paycheck, right, you have your gross pay, which is like this ideal number, you'd like to keep all of it, and then there's all that government extortion, okay, taxes, EI, all that kind of crap, CPP that comes off that you have to pay, okay, then there's your net pay, that sad number that you get to keep. Okay, after the end. Okay, so it's just like that. Net is after everything's been deducted or added together or whatever. Okay, that's what's left. Right? It's why you could do something like this. If you had a stack of like checkers or poker chips or something like that, okay, and you flicked one at the bottom of the stack, and you did it fast enough, you'd be able to knock the bottom of the stack out, and the rest of the stack wouldn't move because there'd be no force on these other ones. Okay, just on the bottom of it. It's the same as the trick where the magician pulls the tablecloth out from underneath all the dishes. Okay, that's a Newton's first law trick as well. Okay, the trick to that is that you have to pull in such a way that you have, well, first off, very slippery dishes and a very slippery tablecloth. Okay, you're not doing this with a cloth tablecloth in your mom's best china. Okay, so if you're going to try it, get like the dollar store picnic table vinyl one. They're really slippery, and some plastic dishes. Okay? Now, the other thing is that when people try that tablecloth trick, they grab the tablecloth and they do this. And they lift, like, up and away. And all it does is lift everything on the tablecloth up and tip it over. Okay? If you watch a magician do that trick, they grab it, they push it against the corner of the table and pull down. That way the tablecloth slides straight out from underneath the dishes. There's a trick to the trick. Okay? All right. So, remember, guys, that net force is also a vector quantity. We were talking about that here with these two forces. The net force was 2 newtons to the left. Okay, so a net force can cause a bicycle to pick up speed quickly, but if the same force is applied to a freight train, any resulting change in motion might be imperceptible. Okay, so we say that the train has more inertia, and inertia is dependent on mass. Okay. Okay, so quantitatively, okay, the inertia of an object is measured by its mass. Okay, so inertia is the natural tendency of an object. That's an important one. Okay, natural tendency of an object to remain at rest or in motion at a constant speed along a straight line. Okay, the mass of an object is the quantitative measure of inertia. Right? The more mass you have, the more inertia you will have. Okay. Okay, now applications. You may not realize this, but the way your seatbelts work actually depends on Newton's first law. Right? Inside of the mechanism that stops your seatbelt from pulling out, you know that one that's always annoying when you're in a hurry? Right? You try to get your seatbelt on, jerk it really quickly, and it locks, and then you're like, "Argh!" And you're trying to let it go back, but you're in a hurry. And yeah, it's really frustrating. You eventually just have to take a deep breath and let it go back in, and then pull it back out. Okay. What you do is, if you pull it really hard, you jerk the whole assembly enough that the locking bar clicks down and catches the ratcheted wheel that your seatbelt is on. Okay. In a crash, what happens is there's a pendulum. Right? So basically just a mass that's hanging on a pivot point. Okay? So somebody stole my demo. Okay, sorry, this is ghetto physics. It's what happens when you cut money from education. Yes, I'm making a pendulum. I'm making a pendulum out of a drawstring I took out of my own hoodie and this roll of tape that just happened to be in the back. Okay, so if I'm in a car and I'm driving along at a constant speed and I suddenly stop, what happens to the pendulum? It continued to move forwards, right? It had inertia. Okay? When we were both walking at the same speed, it stayed right in front of me. I stop, the pendulum goes forward. Okay? Well, that's how your seatbelt works. That pendulum swings forward and it tips this locking bar into place so that the seatbelt can't unwind. That's what stops your seatbelt in a crash. It can't fail. It doesn't require any power. Okay? If the computer in your car was smashed or anything like that, it wouldn't matter. This depends on something that can't be stopped. Okay? Newton's first law is going to work in this situation, and it's going to cause your seatbelt to take up. Okay? Seatbelt didn't always work that way. Right? Way back when you had just the lap belt, okay? Just the one that went across the waist, and it was just tight. Like you didn't have any ratcheted thing, you just tightened it across your, kind of like the ones in an airplane. Okay? That's the ones that like used to be in every single car. It was just like that. Okay? And the problem they had with them is they could cut people in half. Okay? Like they could literally paralyze them because there was nothing to stop their chest from moving forward. So they would fold. Okay? The ones now that we have to go across your chest stop your chest from moving. Okay? Now your big worry is like a neck injury. Okay? But that's what, of course, that's what the airbag is for. It stops your head from moving forward. Okay? Slows it down. And again, the whole idea of an airbag goes back to this. Okay? What part of this equation does the airbag work on? Time. Okay? It works on time. If you hit the airbag, your head slows down more slowly than it does if it hits the steering wheel. Okay? If it hits the steering wheel, it stops instantly. Okay? If it hits an airbag, it's like, well, it's not a film. It's a punch in the face, but it's not as bad as it hitting the steering wheel. Okay? So you hit that, and your head slows down a lot more slowly than it does if you don't have one. Right? Now, the problem with airbags is that people think that they're as good, but they're a replacement for seatbelts. Okay? And they're not. You can go right over/through an airbag if we're talking about the mass of your entire body. Okay? It's pretty scary to see the contortions that the human body will go through if it's not wearing a seatbelt in a crash. Okay? Like, what happens to all of your joints and bones as you go over the steering wheel and out the window? Okay? Like, basically, all of the joints in your body bend the wrong way. Okay? Your bones basically all break. And then you hit the steering wheel, or hit the windshield, and your neck goes back. Okay? It is terrifying. I'm trying to terrify you. Wear your damn seatbelt. Okay? It's important. Okay? It'll keep you in the car. Because the problem is, guys, is everybody hears about that 1 in a million crash where the guy got thrown out of the car and lives. And if he hadn't been thrown out of the car, he'd have died. He's the 1 in a million chance. Okay? Most of the time, 99.9% of the time, you are better off to stay in the car than to be thrown from the car. Yeah. Okay? Especially, and this is the worst one, in a rollover. Okay? People who aren't belted in rollovers, what kills them? Their car. Okay? Because if you're rolling like this, you're going to be thrown here. Okay? And your velocity is going this way. You'll be thrown that way. Because you're free of the car, you'll move faster. The car is slowing down. So you'll do this, and the car will go over here. Okay? Better to be in the car. Okay? If you're in the car, at least the car's cage can help to protect you. If you're outside the car, you could be crushed. Okay? Most of the time, that's what happens if people are thrown from the car in a roller. They get crushed by their car. You don't want that. In addition to all the problems with exiting a vehicle through a window.
Yeah.
Okay? A closed one, not an open one. Okay? Lots of bad things can happen that way. Okay? This is why, guys, paramedics often have a very short career. Okay? It's hard, like if you've ever been at an accident scene, they deal with that all the time, but if you've ever been at a scene of a bad accident, that's what they deal with all the time. And it's scary. It's traumatizing. And a lot of those paramedics, they have like PTSD really bad. And police officers too, because they're always on scene. Okay? Anyone been on the scene of a bad accident? Okay? I was the first one on scene for a single motorcycle. Okay? Guy just lost it right in front of Fish Creek Nissan. You know where that is there on the McLeod Trail? Okay? He hit some rocks or whatever, he lost it, and he went down, and I watched the bike roll like this. Okay? He kind of, rolled over once, and then he slid to the side and hit the curb. So I stopped and I ran over to the other side of the road, okay? And he was a mess. And in fact, he wasn't breathing when I first got there. I was just getting ready to start CPR, and then he coughed, spit in my face, and because I was like getting ready, and yeah, and he coughs in my face and starts breathing, and then all he's doing is just like moaning and like yelling, and he's bleeding all over the place, and he's a mess, right? And here you are, looking at this, and you're trying to help this poor guy, okay? But he's wanting to move, and you're trying to keep him in one place, and there's all of these other people around freaking out, they're trying to stay calm, okay? Meanwhile, you've run into the middle of the street, an 80-kilometer-an-hour road in the dark, and you just run out there to help this person. What's the first thing they tell you in first aid? Check the surroundings. What are you going to do? You're going to run out there and help the person. You're not going to look. This is what I did. And I just finished my first aid training. And the first thing I did was run out and help that guy. I didn't even look. I could have got hit by a car too. Okay? Right? But your first instinct is you got to go help this person. Yeah, it's crazy. Okay, so tomorrow, you don't have a quiz. We've only covered one thing and there's nothing to test you on yet. So no quiz tomorrow. But listening, please. Tomorrow, remember the listening, please, part? Okay. Tomorrow we're going to start Newton's second law. Newton's second law is half of this unit. It's the most important topic in Unit 2. We're going to start it tomorrow. Okay? So come ready to learn tomorrow. All right, if you guys can move those desks back into the horizontal row, please.